This is a math review on polynomial long division. You need this for several places in this course. I want to start by reviewing arithmetic. Back in around the 4th grade, you should have learned how to divide big numbers by other big numbers. And the technique they introduced was to rewrite the problem in this form, with the numerator inside the bracket and the denominator outside. You were then told to say how many times does 1 go into 2. The answer might be 2 here. You were then told to take 2, multiply it through your 132, then to subtract, and then you could write your answer as a whole number plus a fraction. We want to use the same technique in many places in this course. Alternatively, instead of writing it as a whole number plus a fraction, you had the option to add a decimal point, bring down your 0, and now repeat the question. 1 goes into 2 how many times? You kind of have to watch the 13 goes into 25 how many times. Again, multiply your 1 by your 132, subtract, and bring down the next number. And you can continue this process forever. This should look very familiar. I'm not expecting you do not know how to do this, but I want you to remember this technique because we're going to do the same thing with algebraic terms. Here's an algebraic fraction, a polynomial fraction. Similar to the numeric example, we'll write our numerator inside the bracket and the denominator outside. And you'll ask yourself, x squared goes into 2x squared how many times? Or alternatively, x squared times what gives you 2x squared? Take your result, multiply it through, subtract, and at that point you can write your answer as a whole number plus a fraction. Alternatively, we can continue this process, similar to how we did a decimal for the numeric example. X squared goes into 2x how many times? Or x squared times what is 2x? Multiply, subtract, and we can repeat this process forever as well. We want to use both these techniques in this course in several different chapters. I'll show an example for each of the different forms which you might see this. In Chapter 4, Fourier transforms, here it's the same example as before, but your x is now j omega. Rewrite the problem. How many times does j omega go into 2j omega squared? Multiply, subtract, and you can write your answer as a fraction. From here you can do partial fractions, and you might want to do this if you're trying to invert your transform. In the case of the discrete time Fourier transform, your x variable is e to the minus j omega. So e to the negative 2j omega would be x squared. We proceed as before, putting our numerator inside the bracket and the denominator outside, asking how many times does e to the minus 2j omega go into 2 e to the negative 2j omega, multiply, subtract, and write our answer as a whole number plus a fraction, which is then conducive to partial fractions, which will help you invert your transform. Same algebra, it just looks a little bit different. You also use polynomial long division for the Laplace transform. This looks a lot more similar because we can very easily visualize your s being your x variable. Nothing new, just a new letter. For the z transforms, it's not very different, but there are a few different nuances you need to work with. We still rewrite our fraction and ask ourselves 1 goes into 2 how many times? Multiply, subtract, and we could at this point write it as a whole number plus a fraction, and we could apply partial fractions to that fraction. But with the z transform, we quite often want to continue the route that is the analogy to writing a decimal answer to a division in the initial arithmetic example. We rewrite our fraction the same way we did before. The beginning part's the same, but rather than stopping with a remainder, we're going to continue by asking 1 goes into 2z to the negative 1 how many times? Repeat multiply, repeat subtract, and then repeat the question 1 goes into negative z squared how many times? Multiply, subtract, and we could continue this forever. This series is something that we want quite often when we're doing z transforms, and we would therefore invert by series instead of inverting with partial fractions. I want to draw to your attention another possibility where we take this fraction, the numerator and the denominator, where we rewrite it. So instead of going from order 0, negative 1, negative 2, we go order negative 2, negative 1, 0. Algebraically, this is the same thing as we had in the previous example. When we go to divide, we write the terms out. Numerator still goes here, denominator still goes here. And we ask ourselves, 2z to the negative 2 goes into 9z to the negative 2 how many times? Multiply, subtract, and repeat the question. 2z to the negative 2 goes into negative 11 halves z to the negative 1 how many times? Multiply, subtract, and this also can continue forever. But now our exponents are positive. Sometimes we want this. Not always, but sometimes. And I just wanted to bring this example to your attention.